Welcome to WMTH, the station that rocks the docks and reaches the beaches. I'm your host, Jeff Parent. We're going to be going over partial fractions today. So partial fractions is a way to decompose something like this into separate fractions. But before we do that, let me tell you a little bit about an example of the use of rational fractions, which is this, a rational expression. So this comes to me courtesy of Todd Fedor, teaches math at Berkeley High School, and he's got the 7-day moving average for the number of coronavirus cases in Michigan for the last 50 days here. So I took his data and I fit a little function to it. It's probably a little bit more intense than what we've got, but it does reflect the data pretty well. You can see the curved line that I have here. Let's flash it on and off. There we go. Does reflect the data pretty well. And what it shows is that for a while we're doing really, really good. And then we started coming back up again, which is bad news. And unfortunately, most of those cases are coming through, I don't know, younger folks, millennials. Anyways, be careful out there. But the point I want to get to is if we were to be able to integrate the rate at which these cases are occurring, then that should give us an idea of the total number of cases here. So what do we do when we integrate? Well, we're trying to find the area between the curve and the x-axis, and that would look like this. Now, if you notice, as I move this slider, I'm also getting a new total here because I'm integrating my function from 0 to k. As I increase k, day 20, day 25, day 30, all the way up to day 50. Wow, that's a lot of cases over the last 50 days. Now the total I'm getting from this real quick analysis with my rational function is about 14,850 cases during this 50-day period. If you actually look at the data, and let's see, I got the data here in this Excel spreadsheet. Let's see what the total is. Oh, not bad. Only off by about 20. So pretty cool. So what we're going to do in this section is try and focus on integrating stuff like this. But the first thing that you need to know is how to decompose stuff like this. Because a fraction like this really can be thought of as the sum of two fractions. Now these are linear terms because each of them is a first degree term. So I'll call that a over 3x minus 1 and b over 3x plus 1. And my goal is to try and determine a and b. And if I do that, then that'll help me when I'm trying to integrate stuff like 2 over 9x squared minus 1. Nice. So how do we solve for a and b? Well, there's a couple ways. I'm only going to do one in this particular problem, but there's a couple ways. And let's start with this equation right here. So 2 over 3x minus 1 times 3x plus 1 equals a over 3x minus 1 plus b over 3x plus 1. Now, one thing that a lot of people don't really like is fractions. So I'll tell you what, let's get rid of the fractions. What we're going to do is we're going to multiply both sides of the equation by the lowest common denominator, which is 3x minus 1 times 3x plus 1. And this multiplies here, here, and here. The good news for us is that on the left-hand side, I just get a 2. On the right-hand side, the 3x minus 1 is going to cancel, leaving me with a times 3x plus 1 plus b times 3x minus 1. Okay, not so bad. Now, there's really a couple ways to solve this. And what I want to emphasize first is comparing coefficients, equating the x's and equating the y's. So let me rearrange this a little bit. That's 2 equals 3ax plus a plus 3bx minus b. And let's put the x's together. So these terms. And then everything else is a constant term. So I can put those together. And I'll rewrite things like this. 3, well, the x part I'm going to factor out. So I'll write it as 3a plus 3b times x plus a minus b. So I've got my coefficients of x here. And if you distribute the x, you can see what we got here, right? 3a times x and 3b times x. So it's just a rearrangement of the terms I have here. But the nice thing here is that that allows me to come up with some more equations. All right, so now what I've got underlined here in blue is the coefficient of, well, it's not a coefficient, it's just my constant term. So the constant terms have to be equal. So the constant term on the left-hand side is 2, the constant term on the right-hand side is a minus b. Hey, that gives me an equation. That gives me 2 equals a minus b. So let's write that down. Let's put it down here. 2 equals a minus b. What else? Well, I got another equation. Now there wasn't an x on the left-hand side, so I can think of that as being 0 x's. And that gives me another equation. That is 0 equals 3a plus 3b. Now, you can solve this any way you want. You can use the addition method. You could use a substitution method. You can use your graphing calculator. You could use an inverse matrix. There's a lot of ways you can solve it. I'll just do what looks like comes easiest, quickest. If I multiply the top equation by 3, that gives me 6 equals 3a minus 3b. And add it to 0 equals 3a plus 3b, for a total of 6 equals 6a. And hey, guess what that means? That means a equals 1. And if I substitute a equals 1 in here and solve, then I end up with b equals negative 1. So b equals negative 1. Great. Well, that was a lot of work to get those numbers. We'll see if we can't make that a little bit quicker in the future. Well, what that does for us is it allows us to rewrite this equation using my new coefficients, 1 for a, negative 1 for b. So let's do that down here. Integral of 2 over 9x squared minus 1 dx becomes integral of 1 over 3x minus 1 over 3x plus 1 dx. The nice thing is that you can integrate both of those terms. Now, integrating them is going to require a u substitution. I'm not going to pause to slow down and do that u substitution here. But if you let u equal 3x minus 1, your du term is going to have a 1/3. You're going to end up with a 3 du term. So to replace dx, you'll have to have a 1/3. In any case, that's going to integrate to 1/3 ln of 3x minus 1 minus 1/3 again of the ln of that, 3x plus 1. Let's not forget our constant. You can bring these together. So it's 1/3 times ln of 3x minus 1 minus ln of 3x plus 1. Look, this is fine for what we need. Occasionally, what you'll see is books get a little fancy and use their properties of logs and write it like this, ln of the absolute value of 3x minus 1 over 3x plus 1. That's nice if you can make it so compact, but it's not critical for getting the problem right. All right, so questions on the first one? Looking good there? All right, big thumbs up from the crowd out there. Appreciate that. Thank you so much. Let's try another one. And I skipped out on some U substitution with the last one, so let me do some with this one. In fact, we're going to start out with our U substitution. And let's see, what's our equation in this one? There we go. So we're going to try and integrate 5 cosine of x over sine squared of x plus 3 sine of x minus 4 dx. Okay, let's roll on that one. Well, what I notice here is I got a lot of sines in the denominator and a cosine in the numerator. Now that cosine in the numerator seems like it's begging to be part of a du term. Now, if the cosine is the du term, cosine x dx, what's the u term? Okay. No. All right, no answers on that one. How about sine of x? There we go. Yes. Oh, sorry, I didn't see your hand. Yeah, you got it. Thank you. In any case, with this substitution, you've got your du term right here. Let's see what happens to our integral. We're left with 5 du over u squared plus 3u minus 4. Okay, that looks good. Let's see if we can't work with our integrand. 5 over u squared plus 3u minus 4. And in order to work with that integrand, we're going to have to split it up a little bit. So if we factor that, that's going to be 5 over u. It'd be plus 4 and minus 1. Now for each of these terms here in the denominator, I have to have a partial fraction. So a over u plus 4 plus b over u minus 1. Yeah, question in the back? No, it doesn't matter whether if I put the a over u plus 4 or the b over u plus 4, it doesn't matter. So the order here won't matter. What will matter is that when you're all done, you take your value of a and plug it back in over here, and likewise with b. But how you label it in particular is up to you. So we're going to play the same game here with this one that we do with the last one. That is, we have to solve for a and b. So I'm going to take this equation here and multiply it by the lowest common denominator, which is really the denominator on the left-hand side. So let's just squeeze in LCD, LCD, LCD. And of course, that's my LCD. If I multiply everything by the LCD, quiz yourself. See if you can't figure out what I'm going to get in terms of the solution here. All right, 5. Now the a plus 4 is going to cancel from, excuse me, the u plus 4 is going to cancel from my LCD here. So it's going to be a times u minus 1 plus b times u plus 4, like that. Now the way we solved this before, and the way you're going to have to solve some of these things, is to equate coefficients, and that's fine. So if you wanted to do that, that would look like this. 5 equals AU minus A plus BU minus, or plus 4B. So we put the A's together. 5 equals, well, let's see, the A's. I said put the A's together. I might put the U's together. So it's going to be an A plus a B times u plus negative a plus 4b. Now on the left-hand side, there's no u terms, but that's okay, because that's going to give us one of our equations right here, that 0 equals a plus b. And another equation we're going to get comes from right here. 5 equals negative a plus 4b. So two equations. And again, you can solve those any way you want. Your graphing calculator can solve systems of equations. It's pretty nice. If you hit me up sometime, I'll probably tell you how to do it. Okay, that's one way to solve for A and B. But let me show you an alternative approach that's going to be really, really handy. This equation up here, and let me circle it in a very manly pink. Beautiful. Let's take that equation there and play with it. How about if I set u equal to 1 in that equation? This is an equation that's true for all values of u, so in particular it's true for u equal 1. So if I set u equal to 1, I get 5 on the left-hand side, but a times 0 on the right-hand side, plus b times 1 plus 4, right? 5. So what do I get? I get 5 equals 5b, so 1 is equal to b. Hey, that was nice. I like that. So let's circle that. And let's see what kind of magical colors I can come up with. I'm kind of running out of colors here. Nothing good here. There we go. So 1 for B. Well, that worked out pretty good, but we also need to figure out what A is. Now, when I set u equal to 1, that made this whole term 0, so I couldn't solve for A. But can you think of a value of u that would make the B term disappear so that I could solve for A? What would make that 0? If you said u equals negative 4, good on you. So let's set u equal negative 4. Now the left-hand side is still 5. But on the right-hand side, I go a times negative 4 minus 1 plus b times, well, 0. So that disappears. I'm left with 5 equals negative 5a. And hey, there you go. A equals negative 1. Nice. So how does that help us out? Well, let's take a look here. Our integral up here can now be broken up into two smaller parts, easier bite-sized chunks that we can work with. So integral of 5 du over u squared plus 3u minus 4 becomes the integral of a. Now this is where it's important to make sure that you look back at what you wrote, all right? Because your a might be different than my a, but this number goes over this right there. So negative 1 over u plus 4 plus 1 over u minus 1. All of that du. Now, fortunately for us, we don't really need a u substitution in this one. And that's good for two reasons. One, less work. Two, we're already using the variable u. So how would you substitute u for u? In any case, that becomes negative the natural log of of u plus 4 plus a natural log of u minus 1 plus our constant. But wait, there's more. We're not quite done because we got to go back and realize that u originally was taking the place of sine of x. So this is minus ln of sine of x plus 4 plus the ln of the sine of x minus 1 plus c. And if you wanted to be really fancy about this, you could bring these two together like this, ln sine of x minus 1 over sine of x plus 4. Okay, hopefully we're looking good at that one. Kind of another distinct linear factor term, as I mentioned. Cool. Let me give you a little heads up on something that you're going to face in your homework. And I'll do it most of the way, not all the way. So the integral of 5 over x plus g and x plus h. Let's put the dx up here. Okay, well, this one's a little bit of a mess, to be quite honest. So let's see. Well, we can still break it up. 5 over x plus g times x plus h. G and h are just constants. Could be like 4 and 7, 3 and 2, 5 and negative 3. Doesn't matter. But G and h are constants. And as such, I'll write it as capital A over x plus g plus capital B over x plus h. Okay, we'll play our little game where we multiply both sides by the lowest common denominator. The lowest common denominator is this term right here, x plus g times x plus h. Now when I distribute that, on the left-hand side, everything cancels. I'll be left with a 5. On the right-hand side, this will cancel with the x plus g, leaving me with an x plus h plus b times x plus g. And we'll play our game again. It's not really easy to plug in x equal negative h, so that nice little trick that I let you in on the last one doesn't help us out here. But I can rearrange things. So that's going to be ax plus ah plus bx plus bg. So we're going to put our x's together. So I've got an a plus a b plus a b times x. And then what's left over is our constant term, ah and bg. So ah plus bg. Well, let's see. Let's see if we can't come up with a couple of equations here. Yeah, I think we can, because we got 0x here. So that gives us an equation right away. 0 equals a plus b. And that actually is pretty helpful, because that tells me that a equals negative b. If I move this to the side, negative b equals a. So, okay. What else can I get? Well, I'm hoping that you're getting used to this little trick here. Let's do it one more time. So what I end up with is, let's see, I get 5 equals AH plus BG. But because A equals negative B, or other way around, you could say B equals negative A, then I can replace this and get 5 equals AH minus A times G. Or in other words, let's see, let's factor out the A, H minus G times A. I actually get an expression for A. Okay, so that's my expression for A, and because B is the opposite of that, so B equals negative 5 over H minus G, because A and B are just opposites of each other. So that's kind of a little head start, a little warm up on that. There's really not much left to do there in terms of the problem. Is just integrate it, and it's going to turn out a lot like what we just had. So in case you're curious, you know, test yourself, but you should end up with 5 over H minus G times the ln of X plus G minus the ln of X plus H. That should be your happy ending. Okay, beautiful, beautiful. Yeah, that one's a tough one. So what you should do now, pause the video, go get your favorite beverage, stretch a little bit, check your email, and then come back nice and refreshed, because that one was tough. Any questions on that one before I move on? Okay. Well, that's good. I'm glad you're understanding it. Yeah, it's kind of tough. It's kind of tough. But actually, those are the easy cases. Yeah, no, I'm not kidding. Those are the easy cases. Well, I'm glad you asked. The harder cases are the repeated linear factor case and the prime quadratic case. So let's start with some of those. So let's just get rid of this. And we'll look at the repeated linear factor case. Try that one again. Repeated linear factor case. Okay. Let's look at an integral a little bit closer to the monster that I had to start this video. And we'll write x plus 1. We'll see. We'll do x plus 2 and then x plus 1 squared dx. Wow. All right, so the partial fraction decomposition for this, x squared plus x plus 1 over x plus 2 times x plus 1 squared, is going to start out with this, a over x plus 2, my linear term. Okay. And then the next one would be b over x plus 1. But you notice that this one's repeated. I've got x plus 1 squared. So I'll put c over x plus 1 squared. Now, if this was a cubed, then I'd have another term. I'd put plus d over x plus 1 cubed. Or if this was a fourth power, I'd go even farther, put e over x plus 1 to the fourth power, and so on. But for every exponent above 1, you're going to have a corresponding power in the denominator and a rational term like this. So it's going to keep on going up until you get to that number, starting with the number 1. All right, well, this one's going to get a little bit messier, but we'll see what we can do. Any suggestions here to solve for A, B, and C? I'm hoping you said multiply by the LCD, and that's my LCD. So I'll multiply by the LCD here, LCD here, LCD here, LCD here. That LCD is going to multiply everything. And being the helpful guy that I am, I'll clear up the left-hand side for you. There you go, x squared plus x plus 1. Beautiful. All right, I guess we need to do the right-hand side too. On the right-hand side, and maybe a few of you would prefer that I actually write out the LCD, so let me squeeze it in here. Let's get rid of these. So maybe kind of see some of that cancellation. Maybe that'll help out a little bit. So I've got x plus 2 times x plus 1 squared, x plus 2 times x plus 1 squared, and x plus 2 times x plus 1 squared. Now on the left-hand side, the whole thing cancels out. But on the right-hand side, let's see what happens. In the first one, the denominator cancels out and leaves me with a times x plus 1 squared. In the second one, just one of these cancels out, so it leaves you with x plus 2 times x plus 1, and that's it. X plus 2 times x plus 1. And finally, in the third one, the x plus 1 cancels, or x plus 1 squared cancels completely, so it leaves me with c times x plus 2. C times x plus 2. Yay. Now, this holds true for all values of x. So let's milk that and see what we can do. You could equate coefficients. You'd have to FOIL this out, distribute, equate coefficients. It would take a while. It wouldn't be fun, but you could do it. You could figure out, you'd have an ax squared, a bx squared. So you'd have a plus b equals 1, which is a coefficient here. And then a lot more work to figure out the coefficient for x, because you'd have a, b, and c terms all having something wrapped up with the x. So let's be clever about this one. Let's see. If I set x equal to -1, then this term and this term are going to vanish, right? Because -1 plus 1 is 0. That'll vanish. -1 plus 1, that term vanishes. The only term that doesn't vanish is the c term. So let's do that. Set x equal -1. Now the unfortunate part for us is that we don't have a nice constant on the left-hand side like we did earlier. Here we actually got to plug it in. So it's going to be -1 squared plus -1 plus 1 equals a times, well, let's just call it what it is. It's 0 plus b times 0 plus c times -1 plus 2. So, okay, well, that's cool. On the left-hand side, 1 minus 1, 0, plus 1 is 1. So we get 1 equals, well, c. That's cool. So let's keep track of that. And I want to play this game again. So let's see if we can't play this game again. What's another value that would help us out? Well, I already used -1. How about -2? If I set c equal to -2, then this term and this term will disappear, but not this one. So let's try that. I said set c equal to -2. I meant x equal to -2. So that's going to be -2 squared plus -2 plus 1 equals a times -2 plus 1 squared plus b times 0 plus c times 0. Let's see what we get. On the left-hand side, that's going to be 4 minus 2 is 2, plus 1 is 3. On the right-hand side, that's going to be -1 squared, which is 1. Hey, that's not so bad. A equals 3. And finally, I need to figure out what b is. Now, I've already used x equal -1 and x equal -2. There's no more choices here that I can use that are going to help me out because, you know, either -1 or -2 are going to cancel that out. But here's what I can do. I know what a is. I know what c is. Let's plug them both in. So let me rewrite this for just a second. That's going to be x squared plus x plus 1 equals 3 times x plus 1 squared plus b times x plus 2 times x plus 1 plus c, which is 1. So it's just going to be x plus 2. Now if I set x equal to some value, the only unknown in this would be b. So let's see if we can't choose a particularly easy value for x. And I'm going to go for x equals 0. Because that's going to be 0, that's going to be 0. I'm going to get 1 equals 3 times 1 squared plus b times 0 plus 2 is 2. 1 plus 0 plus 1 is 1 plus 2. All right. So let's see what happens here then. I get 1 equals 3 plus 2b plus 2, or that's 5, bring it to the side. -4 equals 2b. Voila. You got to tell me next time I go off the screen. I'm sorry. Didn't realize that. Not bad. Not bad. So what does that tell me about my integral? Well, that gives me my values of a, b, and c. You have to be careful to put those up on top of the correct term. So a goes over the x plus 2 term, b goes over the x plus 1 term, and c goes over the x plus 1 squared term. So let me see if I can't get those straight. That's going to be the integral of x squared plus x plus 1 over x plus 1 squared times x plus 2 dx. And yeah, I changed the order on that, sorry. Still the same function. That breaks up into the integral of a, which was 3, over x plus 2, plus b, turns out to be minus 2 over x plus 1, plus c, which was 1, over x plus 1 squared. And all of that's got a big dx around it. That dx. Well, we still haven't integrated it, but we're to a point where we can integrate it pretty easily. The only thing you got to be careful of is this term here. And have a little, might need a little u substitution. So let me grab a new sheet of paper and finish that one off. Let's see, that's going to be 3 times the natural log of x plus 2 minus 2 times the natural log of x plus 1 plus the integral of x plus 1 to the negative second dx. I'll give you a little trick here. Back in Calc 1, we'd probably make a u substitution, and u would equal x plus 1. And what you'll find is du equals dx. If, in thinking about a u substitution, if du equals dx, you know what? You don't really need to formally do the u substitution. Just integrate it the way you think it would be. Remember what we do with stuff like this. What does our power rule say? Our power rule says add 1 to the exponent, divide by that same exponent. So it's going to be x plus 1, the negative first, divided by negative 1 plus a constant. We can get away with that if du equals dx. All right, not just everywhere. Now this cleans up a little bit. I'm going to leave this here the same, 3x plus 2, or 3 times the natural log of x plus 2, minus, with the minus there, this is going to come down to the denominator, 1 over x plus 1 plus a constant. Beautiful. All right. Let's take a look at another repeated linear factors case. And I'll make this one a little bit easier for us. Yeah, should we make it? No, I guess I'm curious as to how many more of these you want. Let me just flash a quick one up in the notes here. And I'll put this as part of the scanned in version here. So again, another repeated linear factors case. This time you've got x minus 2 squared in the denominator. So that means when you set up your equations to solve, you're going to have an x minus 2 and an x minus 2 squared. And then you need to figure out your partial fraction decomposition. How does this decompose into these two fractions? Cross multiply, well, multiply everything by x minus 2 squared. That's going to leave this. One of those will cancel. 2 of those will cancel, leaves you with a b. For a couple clever choices of x, you can solve for a and b. First by setting x equal to 2, then that disappears. You're left with b equals 8. Great. If b equals 8, plug that in here, solve for a. Another clever choice would be x equal 3, because 3 minus 2 is 1. Get to solve for a pretty quickly. You get a and b are 5 and 8 respectively. Plug that in and integrate. So there's kind of a freebie there for you. All right, but the one I want to get to a little bit harder, it's going to look like this. Integral from 1 to 5 of x minus 1 over x squared times x plus 1 dx. Well, this is another partial fraction decomposition problem. So it's going to be x minus 1 over x squared times x plus 1 equals And let's set up a couple terms. I'm going to have an a over x, but I'm hoping that you notice that the x is repeated. So what other term would I need here? All right, thank you. Yes, b over x squared. If this was a cubed term, then I'd have a plus c over x cubed. It's not, because that'd be an insane amount of work if I started making this cubed in higher powers, but you could. Fortunately, your instructor is a little bit kinder. This is a kinder, gentler math class. Last but not least, we have that plus c over x plus 1 term. And you seem to like it last time when I wrote in everything. Maybe that'll help you out. We're going to multiply everything by our lowest common denominator. The lowest common denominator is going to be x squared times x plus 1, x squared times x plus 1, and x squared times x plus 1. So x squared times x plus 1. Lots of cancellation. Here, everything cancels, so it leaves me with x minus 1. On the right-hand side, just one of the x's cancels. So, okay, I'll get rid of you and you. It's going to leave me with a times x plus 1. And let's see what happens over here with the b's. Well, with the b term, the x squared completely cancels, so I'll have b times x plus 1. And last but not least, c. With c, the x plus 1 term cancels. I'm left with c times x squared. So you should get that equation out of this. Now, I'd play that same game all over again. See if you can't figure out clever values of x to choose to help you solve here. Maybe you want to pause the video for a second, see if you can't figure out what you'd set x equal to. At least the first two. All right. So my first one here would be x equals 0, because that'll get rid of this term and allow me to solve for b. So if I set x equal to 0, that's going to give me 0 minus 1 would be negative 1 equals a times 0 plus b times 1 plus c times 0. In other words, negative 1 equals b. So that was a good choice. What's another easy choice for x? All right, I think I heard a couple people out there saying negative 1. Good job. If I set x equal to negative 1, coming back up here, we get negative 2 equals, well, a times 0 plus b times 0 plus c times negative 1 squared. Negative 1 squared is going to be 1. These two terms disappear, so I'm left with negative 2 equals c. 2 down, 2 to go. Let's keep track of these. Here and here. I said 2 down, 2 to go. 2 down, 1 to go. Now that last one, we're going to have to work for a little bit more. So what I'm going to do is I'm going to replace b and c up above. So if I do that, then I get x minus 1 equals a times x plus 1. And let's see, b was negative 1, so it'll be minus x plus 1. And then c was negative 2, so it'll be minus 2 x squared. Great. Now I'm free to choose any value that I want for x. I'd probably avoid 0 and -1, but other than that, any value will work. Keeping it simple for myself, I think I'm going to choose x equal 1. Set x equal 1, because on the left-hand side, that'll just give me a 0. That's easy. On the right-hand side, it's going to be a times 1, which is 1, or it's just a, and then times 2, and that'll be a minus 1 plus 1 is 2, minus 2 times 1 squared is also 2. So that's really a minus 4. Bring that to the left-hand side. So plus 4 equals 2a. And that tells me that a equals 2. Whew, there we go. A, B, and C. Let's put those back into our problem and finish integrating. So be careful to line it up. A goes over the x, B goes over the x squared, C goes over the x plus 1. So the integral from 1 to 5 of x minus 1 over x squared times x plus 1 dx. And that's going to equal the integral from 1 to 5. A was 2, so it's going to be 2 over x. B was -1, so it's going to be -1 over x squared. And C was -2. And I'll just write the negative here. -2 over x plus 1. And all of that is dx. We can find the antiderivative of all these things. So let's do that. Let's change our integral to a straight bar as we move from the integrand to the antiderivative. And the antiderivative here is going to be 2 ln x. I don't really need the absolute value because both of those are going to be positive, so I'm going to be lazy about that. Plus 1 over x minus 2 times ln of x plus 1. Again, I don't really need the absolute value. Can anyone tell me why I don't need a constant here? I don't need a constant because it's a definite integral. So I wouldn't have to fuss with it. Plugging in the upper limit is going to be 2 ln of 5 plus 1 over 5 minus 2 ln of 6 minus 2 ln of 1 plus 1 over 1 minus 2 ln of 2. There is a little bit of good news for us here. That's 0. 1/5 minus 1 is going to be a minus 4/5. So I'll get that out of this. Those together give me a minus 4/5. And if you play around a little bit, you can clean up the logs. We've got 2 times log of 5 divided by 6. And then you got a plus ln of 2. That all can combine. I'm not going to bother showing you all the fancy little details with your logs, properties of logs. We'll end up as 2 natural log of 5/3 minus my 4/5. Beautiful. Okay. I know you're getting tired. I am too. But just a couple more here, and then we can be done. If you'd like, take yourself a break. Some of the research that I've read says it's really a good thing to take a break and not to just mindlessly study. Your brain actually needs time on and time off from a task. Think of it this way. Think of it like building a wall out of cement bricks. So if you're building a wall, you're building, adding some bricks in layer by layer. All right, so not the fanciest bricks, but in between each layer goes some mortar and so on. Now, the thing is, if you build it too high and build it too quickly, what happens? The mortar doesn't set. And if the mortar doesn't set, then when you add on more and more layers, this whole thing is just going to come crumbling down. So the time you spend away from things is just as important as the time that you spend on things. You need time on and you need time off. And occasionally when you're away from your books, one of the things you can do is try and recall a picture of a problem that you did, or just actually the calculations, and try and do it in your head. If you can repeat the calculations without having to write it down, without looking at it, then that's great. That's the real heavy lifting that's going to cause some great muscle memory, and you're going to ace that test. So good on you. Okay. Hopefully that was a little bit of a break for you, because we do have some more to do. 6. Okay. Let's kind of ease back into things this way. Before we do the prime quadratic case, let's do kind of a fluff problem. But it's going to require that you're going to know some division, some synthetic division. So if you look at my website, my YouTube channel, I've got a video on synthetic division right next to the video for this one. You might want to review that. But let me show you where you would need synthetic division. Suppose you have something like this. Anytime you have a rational expression in which the numerator is bigger than the denominator, then the first thing you want to do is divide. You want to make this so that the numerator is lower in degree than the denominator. Now, we can do that synthetically. And let me give you a quick reminder. This problem can be thought of as x to the 4th plus 0x cubed plus 0x squared plus 0x plus 5 over x minus 2. And the reason I wrote it that way is to remind you that synthetic division works with all the coefficients. So the coefficients here are 1, 0, 0, 0, and 5. Now out in front is the number that makes this denominator 0. Synthetic division works, by the way, only when you're dividing by x minus something or x plus something. So basically you got to change the sign on that term there. I'll draw a little bar there because whatever this is going to be my remainder. Synthetic division works by add and then multiply, add and then multiply. Now this first step gets a 0 always. Just accept it. Add going down gives me a 1. Multiply. 2 times 1 is 2. And then repeat. Add going down, 0 and 2. Then multiply. 2 times 2 is 4. Can you do the next one? Try and beat me. Add going down gives me a 4. What am I going to put up here? 2 times 4 is 8. Add going down. And then 16. And finally 21. Now the important thing is, well, what does all this mean? And if you don't know that, then the rest of this is worthless. This is your constant term. That's your coefficient of x squared, coefficient of x cubed. And it makes sense if you divide x to the fourth by some power of x, or some term in x, that you're going to end up with an x cubed term. Okay, just subtracting exponents. 4 minus 1 gives me 3. That's actually really helpful. This is my remainder. So when I put all this together, I can write that as x cubed plus 2x squared plus 4x plus 8 plus 21 over x minus 2. And now this is easy. This is stuff that you could have done in Calc 1. X to the fourth over 4 plus 2x cubed over 3 plus 2x squared plus 8x plus 21 times the natural log of the absolute value of x minus 2 plus a constant. But it all relies on synthetic division. Like I said, if you need a refresher, you should find a video next to this in the playlist that'll help you out. All right, so shameless plug for my other videos aside, let's look at the last case here, and these are prime quadratics. And we've got 2 of these. The last one is just an example because it's just like your homework, so I wouldn't blow off the last one. Prime quadratic. You're not going to be held responsible for that, just so you know. The reason I mention it is because these are just different classes of functions that we can factor with this partial fraction decomposition. Actually, if you look carefully at this, what this is, it's the factorization of x cubed minus 8. That's where that comes from. Now, if you tried to factor x squared plus 2x plus 4, then you're not going to go very far. It's not going to break up into linear terms. I should probably put a dx here. That'd be nice. So what's the partial fraction decomposition going to look like? Well, this term should be pretty predictable. You've got a linear term here. So degree 1 term here, you're going to have something of 1 degree less in the numerator. So it's going to be just an a, which is a constant term, or degree 0. So you go from degree 1 to degree 0. But for the next term, x squared plus 2x plus 4, that's a degree 2 term. So in the numerator, you're going to have something of degree 1 less, and that's going to be a degree 1 term, or a linear term, like that. And that's your partial fraction decomposition when you have a prime quadratic. Quadratic that won't factor in the numerator, you're going to have to put that linear term. Okay, so I want to focus on the setup. I'm not going to spend as much time on the actual calculation of A, B, and C. You are going to have to multiply both sides by the LCD. And what you'll end up with is everything on the left-hand side canceling. When I multiply this times this over here, that term, the x minus 2 will cancel, so I'm left with a times x squared plus x 2x plus 4 plus bx plus c times x minus 2. Now, you can play some nice games and set x equal to 2. X equal to 2 will get rid of those and allow you to solve for a. And what you'll find is that a equals 1. Then what would you do? Well, if you set x equal to 0, that'll knock out the b, you know a, so that's another helpful one. If you set x equal to 0, then you're allowed to, or then you'll be able to solve for c, and you'll find c equals 2. And if you set x equal to 1, after plugging in b and c, you should be able to find that b equals -1. Okay. So there's a little bit of a trick here in the integration, which is what I want to get to. So let me rewrite the integral using my values for a, b, and c. So it's going to be the integral of 1 over x minus 2, no problem there, plus -x plus 2 over x squared plus 2x plus 4. And that's all dx. Now what's really close, really kind of tempting here is a u substitution here. I mean, that almost looks like the log. Let me show you what I mean here. So if I let u equal x squared plus 2x plus 4, then du would be 2x plus 2. Du is 2x plus 2 times dx. And it's tantalizingly close to what I got here. In fact, I could factor out the 2, which leaves behind x plus 1. If I could just do something a little bit different here, if I could maybe tweak that, then I can make a u substitution. So, okay. Du, like that. So let's see. If I could factor out a negative here and have an x plus 1 term left, I'd be in good shape. In fact, what I'd like here is -x plus 1. Now let's see what's happened. I've changed the plus 1 here, or the plus 2 here, to effectively a -1 there. So the difference between these two is 3. I manufactured a 3 someplace. Now, let me back up a step. Let me try and do it this way first. -x minus 1 that's what I want here, because I can factor out a negative from that term and then complete my u substitution. But wow, I can't just change this by a difference of 3. So what I'll do is I'll put a plus 3 over x squared plus 2x plus 4. And it may look a lot messier. And in fact, it is a little bit messier, but at least these are things I can now integrate. So this term right here, I can handle with the u substitution. This one, I don't even need a u substitution. I can just get a a natural log term from that. This one's going to require some more work. Okay, so this one, let's just right away write it as the natural log and kind of be done with that. So natural log of x minus 2. And then this one, I've got to factor out that negative, play around with our substitution. So let's see here. If I divide both sides by 2, I get du over 2 equals x plus 1 dx. And that's close to what I have here. If I factored out the negative, yeah, if I factored out the negative, I'd be in good shape. So let's do that. I'll factor out the negative and leave behind x plus 1 over x squared plus 2x plus 4 dx plus the integral of 3 dx over x squared plus 2x plus 4. So this one I can now handle. That one's just a u substitution. I'll put 1/2 du over u, and then I'll get a log out of that. So I'm getting closer to this. ln of the absolute value of x minus 2 minus, let's see, the integral of 1/2 du over u plus this one. I didn't get to cover this in section 7.3 like I would have liked, so you're going to kind of get it now. Just a reminder or heads up. The integral of dx over a squared plus x squared is 1 over a times the tangent inverse of x over a plus a constant. So we're going to rely on that as we work with this. But this doesn't exactly match up here very well. So there's a little trick we're going to play here on our denominator. I'm going to split it up a little bit this way. 3dx over x squared plus 2x plus 1 plus 3. Now, why did I split it up like that? That's because x squared plus 2x plus 1, well, that's a perfect square. So I can rewrite that. Let me do this right here. And we'll continue down. So this is going to become ln of x minus 2 minus 1/2 ln of u. Now, u is this thing right here. X squared plus 2x plus 4 plus my integral right here. Integral of 3 dx over x plus 1 squared plus 3. Now, if you're still with me, you're a champion. I want to see that written in your notes because this is a tough problem. But don't worry, the next one will make this one look easy. All right, I'm kidding. Let's see if we can't force this into this pattern here now. The 3 can come out in front. It's going to be 3. A squared. Well, that doesn't look like a square unless you think of it as a square root of 3 squared, in which case, okay, it's a square. So 3, which comes out of the integral, 1 over the square root of 3, tangent inverse of this term, x plus 1 over the square root of 3, like that, and add that to this, and then add in a constant. All done with that one. So, well done. So if you're still hanging with me, that's great. If I put you to sleep, well, sleep's a good thing too. It's restorative. So let's make that champion squared. All right, so the final answer, let me just kind of circle it like that. Okay. If you're like me, you're probably getting kind of tired, but maybe it'd be helpful to see one last one. And tell you what, I'll just kind of put it up here and then talk through it on the quick. This is another prime quadratic one. You can see that if you factor out the x from the denominator. So you've got an x times x squared plus 3. X squared plus 3 is going nowhere. All right, you can't factor that. It's prime. So that's why you get something like this. You can play some games, multiply by the LCD, and solve for A, B, and C. So 2, -1, -1. That turns this into this. And kind of like what we did with the last one, I'm going to split this term up. The first one, when you split it up, you can use a du term, a u and a du to finish integrating this one. Over here, that's going to integrate as the arctan. So I probably should have led with this one as opposed to the last one. Sorry, not perfect. But once we integrate here, you get the natural log. Another natural log term that you get from our substitution is a factor of 1/2 that comes from our du term, and then the arctan. So yeah, I made a mistake in the order of the last two. I should have started with this one, my bad. But hopefully you'll appreciate that you get the easier one on the test as opposed to the hard one. Okay, big smiley face. We're done.